Thank you much. Thanks for having me. My name is Matthias Sperl, and I'm greeting you today from 8:30 in Germany. Next slide, please. Okay, so that seems to be a preliminary version of the slides I've uploaded and told you that I have more of that. So I tried to have the outline with a couple questions. What I brought here in the abstract is a couple ISS experiments that are relevant for grains and interpretation in different gravity environments. So the view I have doesn't show any outline, but let's move forward. So if you go on a trajectory from Florida to the space station with the SpaceX, you would cross Cologne rather closely. If you look down, there's a research campus of DLR in Germany, and we are in the materials physics. We also do have some life sciences and a new addition to our operations, which is the Lunar habitat, which should be the next picture. On the next slide with a time lapse. That's not what we have here. So what I show here is later in the presentation that we had some collaborations with Penn State, where we have both concrete binder-based materials and most recently geopolymer-based materials that were done in August on the space station. And that was between building materials done by sintering and concrete materials and geopolymers that were done by binders. So I'm a little confused about the sorting. So what's the next slide? So that seems that a preliminary version has made it into the slides here. Title slide again. And in my outline, to take care of grains in extraterrestrial environments, we can do better predictions, better diagnostics, or better mitigation. I showed you where we are. Let me skip the time-lapse video and tell you that we have an exciting opening end of September, and we will be doing comparative studies for binder-based and sinter techniques. We're looking at suborbital platforms. We will have a dusty vacuum chamber like it was shown here in the meeting already for a couple slides, but we will be able to have that flown in drop towers and the parabolic flight. We are interested in fluidized beds, and we do gravity offloading and hope to do that with a rheologically adapted simulant. Legacy from ISS and microgravity research tells us that granular gases, fluids, and packings all have interesting gravitational aspects, in addition to the granular oddities that this non-equilibrium system has in and by itself. I show here quickly some apparatuses that we used for getting our hands on granular gases, granular soils. And I wanted to quickly also mention with my surveyor figure that we have clustering and Maxwell or non-Maxwell distributions in granular gases really having an impact on impacts. And we are particularly proud at the moment to be able to provide some theory-based first principle rheology, where you see on the lower right-hand corner, the full lines are the theory and the data points are done by the respective experiments. So there's no simulation involved here. You can use the theory we're proposing to predict yield criteria. More Kulo is not always right. And we are able to reproduce mu of I rheology, which consists of the upper two equations that result in comparison to our microscopic theory that the first equation is so good that you cannot even see the red line. And on the right-hand side, if you go for the mu of I, it deviates, and you should be able to understand and interpret the deviations, but it basically gives a first theoretical foundation for that empirical law. If you want to test things in 1/6 gravity, you can go for parabolic flights. We have now 2 drop towers in Germany that are linear rails and can do 1/6 gravity, which is quite comfortable. And you see on the upper right-hand side that the slower you go, the more time you have, but you can get about 4 seconds of microgravity as well as lunar gravity for that. I spoke about better diagnostics. So many people are aware of green light for food science. If you want to do similar things for grains, you look at a gap in the frequencies that typical lasers would provide. We addressed that issue a couple of years ago and found that both from broadband and monochromatic terahertz sources, you can get something with 100 micron in the middle. And that allows you to do quite some interesting process engineering that should also be instrumental for lunar applications. One of the funniest things we applied it to was the coffee and the sugar in the lab, and we found that the coffee was clumping. Coming now to mitigation, we have, in addition to laser sintering, which is shown as a simulation on the lower right-hand side, where we both look at the granular and the metallurgical aspects. Concrete as a reference material, where we had Matthias Maurer, the German astronaut, doing it 2 years ago, and Matthew Dominic doing it 2 weeks ago on the space station, where we look at concrete as a reference material. We're not proposing to do everything with a lot of water on the moon. We are trying to save water with geopolymer solutions, and that is at the same time saving CO2 on Earth for similar compositions. We look at the 3 sintering techniques I mentioned up there, and we can combine that on our campus with in-depth material investigations. So this is what you have seen before. We had quite some good collaboration with NASA's BPS division and Penn State with Ms. Radlinska, where we had binder-based, sinter-based, mostly concrete-related research, and the arrow will continue into the future, and we're very much looking forward to that. And I want to conclude with mitigating by textiles that we can produce from fibers. Here on the left, you see with the man over 3 stories how that is typically done in industry. Our colleagues from Fibercoat and the RWTH Aachen managed to do that in a small cube that can be brought airborne, and that is able to produce fibers like you see it on the right-hand side. If you make textiles of those fibers, you can make plume tests that are currently ongoing. So I may be able to show that in a few weeks' time. And concluding, I wanted to thank you for having me again. Appreciate being part of the Isaac G gap analysis, where we had a lot of interesting discussions of what still needs to be done, and stress that I both enjoyed and hope for more international collaboration. Thank you very much.